up here to the top, and you can go to design and quick layout. And that's my quick layout. It's my favorite one. You know, it's the chart title, it's all this stuff. I think also, I'll show this again real quick. It's got all these options, it's got so many cool things, it's so nice.
Gary! I was just looking for the sports channel, Gary.
Hey everybody, how are we doing? We are live. If you're here with questions, let us know. There was short hair Brian a second ago. Long hair Brian is back. So let's see. We've got stats 201, 320, 474. I might start talking a little bit about 320 right here. 474, if you hop in the room, let us know. But if you are here and you have questions, we can take any questions. Let's hop here to the main screen. Let's do it. Okay, so we're here on the main screen. And let's start talking a little bit about models for 320. If you jump in the room, let us know. We're going to load up here library reg class. A little bit of talk about 320 right here, maybe reviewing conditions for models and stuff like that. So let's talk about how to do conditions for models. Checking conditions for models. If you are in the stream, let us know. We're just loading reg class right here. Data survey 10. Let's predict someone's GPA from their height. And we're going to do y tilde x comma data equals and survey 10. Just so we can remember the way this works is the first thing we are storing into is the name of the model. This is just, it can be any model name. So this code will also run. It'll just call it model, like this calls it M. So what we call right here is arbitrary. It's just the name of what we're storing. Usually just pick M because it's simple. It's something easy to store into. If you want to call it model 1, you can always call it model 1. I'm going to clear this real quick. So that way we don't have to see all that. We can just look at this right here. But we should know that this is the name of our model. That is what we are creating. It's an object we can then manipulate. The LM stands for linear model. The model we are creating here is a linear model. GPA is the Y variable. Height is the X variable. And this is the data frame. A data frame is just like an Excel spreadsheet. So it has the variables inside of it. So this is where we're getting our variables from. So let's reverse time right here and run the model again. We're just storing it again. And now we can visualize it. Now the first thing we want to do is just look at our model. This is what I do originally just to make sure if the model actually looks decent. Actually, it doesn't look that bad. Does not look that bad. And if you notice, we got the location of the legend, not lock, but loc. I'm just going to move it out of the way so I can view this. I just took the legend right there and moved it off the screen. It moves it to the Y location. So I said send it to location 9999, which is way above. And now we no longer have that blocking our view. For the most part, I do see a kind of homoscedastic, same spread. The linear model looks to be good. It just looks to be a weaker model. R squared is going to be pretty small, maybe about 8%. 8% if we're lucky. So, yeah, maybe 8%. Let's guess. Let's say 8%. Oh, yeah, not even that much. 2% if we're lucky. So it does look to be pretty weak, but the regression conditions might hold up. So it is statistically significant, this model. This whole model here, the line we created, is statistically significant, which means the reduction in the sums of squares error we are observing is unlikely by random chance. We see that very little variation is explained, but let's check our conditions first to do the regression. Check regression M1. Let's take a look. And there are some problems. The question here is how many problems are there? So we have to look at the p-values. Now, usually people think high p-value is bad, low p-value is good, but high p-value just means fail to reject the null. Low p-value means reject the null. When the p-value is low, reject the null. So what do we see here? Low p-value, high p-value, low p-value. Now, when is the p-value low? When it's below 0.05. So our 3 steps right here, and we should make sure we understand them very well. Let's write down the 3 steps. Steps for checking regression. Step 1. Look at p-values to see if any are below 0.05. If any are below 0.05, you fail those tests. Step 2. Look to see if the sample size is greater than 25. If it is, that's a sentence. If it is, you can continue. If not, stop. So these are the first 2 steps right here. We're going to see if we fail any tests. Let's look. We fail the test for the linearity. So there's a problem with this line, and we failed to test for the normality of the residuals. So we have to look to see if we have a sample size more than 25, which we do, 25 or greater. So we can continue now. If we had less than 25, we must pass all the tests. So we get to continue. We get to continue on and see if we can use this regression. So step 3 is to examine the relevant diagnostic plots to see if we are okay. Now, this is maybe the hardest part because you have to know how to read the plots. So when we go to these plots, we have 3 plots right here. The first plot, all the way over here, is for the linearity, which is this line right here, and for the equal spread, which I don't really see equal spread issues, and we passed that one. I also don't see this line not going through the middle of the data. This line right here looks to relatively go through the centers of these points, but the big problem is the normality of the residuals, and I have to vanish for a second. The big problem is going to be the normality of the residuals. There's a huge problem with these low outliers down here. You notice it right here in the QQ plot for normality, and this is why the p-value for this test was so insanely low. There's very big problems with the normality of residuals. People ask, what are you going to put on the test? This is probably one of the top questions I could put on the test right here because it so readily shows a horrible QQ plot. Without a question of the doubt, this one probably, I'd say, has big problems with these low residuals, i.e. they're over here in this QQ plot. I would not use this due to the problem with the normality of the residuals. So the third plot is where we look at the normality. If it follows the red line, it's good, and it doesn't follow the red line, so it is bad. It is not a normal QQ plot. We could get more normal plots. I could show a better one. Sometimes finding a good regression is hard to do, and so let's go get a better one. I think EX4 bike might have decent. Let's do demand. I know the names of the variables if you're wondering. And let's do AVG temp. And that's the wrong data set for them. That's why it won't run. And now that works, and we can just redo. We can see the plot. A little bit of plot thickening down here, and if you notice, the 999 is showing up right there. So let's just move it to 99. That'll be off. Oh, there's 99. Well, let's go to 9999. There, it's gone now. I just don't want to see that because we're not talking about confidence or prediction intervals. I just want to see the regression as a plot. There's a little bit of outliers right here, outlier here. Not that any point outside there's an outlier. It's just that 99.7% of points would probably be between the prediction intervals. The bigger issue I see, there's a little bit of nonlinearity too. Do you see it? Do you see how the points are low here and then they go low again? There's kind of a little bit of a up and down through that. We can really see that if we want by going here and going to choose order, which we haven't done officially yet, but it's a great way to see the non-linearity of a model. And also we can move the location off of that. I think it still responds to this. There we go. I do see some non-linearity. So we're probably going to fail the test for linearity because a polynomial model has a much better fit. It goes through the data a lot better than the line does. The line does not look to go through the center of the data at all points. If you see right here, it's too high, and here it's too high, and then it kind of bends around it. So we're probably going to have problems with the linearity. I'd be shocked if we don't. Wow, we just barely don't. That is shocking that we just barely don't fail the linearity. So much for a visual inspection. We do not fail the linearity. What we do fail, though, is the normality of the residuals. So we passed all tests except for the normality, which means it's time to look at the plots. And this one does a bit better. If you compare it to the last one, if you remember how our last one looked, like rewind the tape and take a look at this QQ plot right here, it's way better. It fails still. It has a p-value below 0.05. So we still have issues right here, but this QQ plot is way better. So once again, to do the steps officially, you want to look at the p-values, see if any fail. And you only have one p-value that fails right here, the normality fails. So that we're going to have to look at the normality of residuals right here in a moment if we have a sample size of at least 25, and we do. Those were the steps right here that I am doing, and just following along to make sure we pass. So now when we look at the normality of the residuals, which is this plot right here, this is not the linearity, not linearity, this is normality of residuals. When we look at the normality of the residuals, we see that there is slight issues on the low side and slight issues on the high side. There's some outliers there. Those are those 3. Overall, I'd say it's pretty decent. I remember catching up on the first 10 minutes. I was confused on what log is and how to see if it, yeah, sure, awesome. Let's talk about transformations here because we could try to transform this model. So if we are trying to see if the log-log transformation is a possible model transformation, it gets mad all the time. It says figure margin's too large. So really, I think if I go smaller font, there we go. So the log-log transformation would be log here and log here. Awesome. No worries. Explaining now. So the log-log model, if you run fine transformations, would appear here as log-log. There it is right here. That is the log-log model. We actually got it to appear as one of the suggestions for this model. So the log-log model is just log 10, and you would take the log of both variables, and it is increasing the R-squared a decent bit from 31.8%, and the log-log brings it to 39%. But to know if the log-log is a possible transformation, you would observe it here with log 10, and that's how we can identify the log-log is a suggested transformation. We can see our model after the transformations. We still have some outliers, but it's creating a higher R-squared of close to 41% right here. So much better models with the transformations. You lose interpretation with transformation. It's harder to interpret a transformed model than it is a non-transformed model. So I'm almost against transforming unless it gives a really good R-squared increase. It's kind of personal opinion. A lot of things in statistics are like, well, choose what you want to do. There's all models are wrong. Some are useful. So, what model are we going to use? That's the big question in statistics. So this is how we get the transformations and we view them. If we want to save one of these transformations right here, so this is how to create the transformation. Let's talk about dealing with transformations. So if you want to use one of the transformations, you would simply take your y variable right here, which is demand. So we would go to y transformed, and we'd go to log 10 ex4 bike $demand, and then we'd go to x transformed. I don't know, I'm not writing these. Log 10, and then ex4 bike $avg temp. And then we're going to create our transformed model right here, and model 1 transformed, and we're just going to take y transformed and x transformed. Now these are not in the data frame. I could have appended them, but I didn't. They're just vectors in the global environment. If you see they're right here, that's why I'm not accessing them in the data frame. They're not in the ex4 bike data frame. They're just here all by themselves. And don't worry, that's a graphics error. It appears all the time. And so that, you see if I run it again, it doesn't appear. I think it's just a plot window thing, so don't worry about it. We can visualize the model. It's the one we saw earlier. Really? Oh, it's M1. I should know what I type. And there's the model. And it's got some... We're not going to pass normality of residuals on this. With these extreme outliers, I said the linearity was bad in the last one, but let's see. The outliers right here are going to cause a big problem when we check this regression. I'd be shocked. And yeah, the normality of the residuals, it's not as horrible as I thought it'd be. It's really just got these extreme outliers. I mean, overall, it's really just due to these extreme points. You can't see them in the plot. There they are. These extreme points right here look to be mainly the problem. I do see a problem moving through the plot, but overall, it's the outliers mainly doing it, causing the non-normality. A little bit of problem at the high side right there, a little bit of problem. But yes, good stuff. That is how we do it. That's how we examine it. And that's how we do transformations. So we're able to transform the model. Perfect, that helps out in the homework as long as I made my model correct. Yeah, as long as you did that, you should be good. So no worries right there. So much stuff. With that, let's see. Summary of M1 transformed. So with this right here, we've got our summary of the model. We have our coefficient of the intercept and our coefficient of the slope variable, which are just your B0 and your B1. And if you want to write out this model, let's write out this model right here. Let's say writing out the regression model transform. So when we write this out right here, we would have that the y variable, we have here demand, which was log 10 of demand. So it'd be here log 10 of demand is equal to And then we copied that. And then it's going to be plus this times, and then the x variable, where was it? Oh, I log 10 did. Well, I did log 10 model. We should have done this right here, technically. So let's do the log model. We did the log model, if anyone's wondering. So we did the log model. And so now we'd have the log 10, so it's times the log 10 of AVG temp. And so what we have right here is this model we can raise to the 10th power. So you really don't, and that's the way you undo logs right here, is you raise to the 10th. You don't have to, well, I guess everything can be undone, but simply the easiest way to do this, to undo the log, let's show right here. If we were to take this, log 10 of AVG temp, and there it is right there. Let's bring it over here. And all we're going to do to untransform this, if you think about how we can untransform stuff, we'd go here and we'd raise this to the 10th, and we'd raise this to the 10th. Like, it's what we raise it to in the power. Now, when these two, what is untransformed to? I think I'm almost in real time. Yes. So untransforming is just solving for the y variable. The whole point of this is to solve for the y variable in the context of the problem. So if you were to cancel these two out right here, you'd have demand equals to, and then you would just have all this right here equals to everything right here. And you don't have to worry about, you can multiply it out, you can do what we need to do with the 10th power, but this all right here is what you could just solve for. So the whole goal of untransforming is to do what? It's to solve for the y variable. So we've got the untransformed slides on here, but the whole goal of untransforming is just to solve for the y variable. So when you think, why do we untransform? It's just to solve for the y variable. And so we should see that here on the slides in a second. Just solve for the y variable. Don't worry about putting the x in a certain spot. It can be on the bottom. It can be totally obscured. If the graders grade it weird, just tell me, but we solve for the y variable. That is the goal with untransforming. So does this make sense right here? The raise to the 10th cancels with the log. I know logs are kind of weird. We don't use them all the time, but this is the log 10 of demand. And if we raise 10 to the log 10, then we get the two canceling right there. They cancel right here and they go away. And then you're just left with demand. So that is how we do it. Timothy, what questions do you have? Mubot is here. No one's talked to Mubot today. Mubot's like, why is no one talking to me? Timothy, what questions do you have? Do you possibly go over number 6 on, yeah, BS474? Let me pull that up right here. Good questions. Great questions. Let me go get that assignment. Number 6. I'm trying to remember what number 6 is. We got the A rules posted. Okay, here we go. Make this bigger right here. And number 6. From the dendrogram, it's reasonable to choose 5 clusters. Add the cluster memberships to the data frame to the scaled, which contains cluster identities from the cut tree. When 5 clusters are found, use table function to show the number of each students in each of the 5 clusters. So we need to first make a dendrogram here, which we should have right here, making the dendrogram. And then we should be able to cut the tree, which this right here is going to be the hierarchical clustering, plot the hierarchical clustering, and then cut tree is the function to do it, to cut the dendrogram. So what is a dendrogram? A dendrogram, let me pull up the notes here so we can see it all and review. A dendrogram is a way of agglomerative clustering. We're going to bring stuff together here with the dendrogram, and we just need to cluster the data. Now, I made a mistake in one class. It wasn't a big mistake, don't worry. I was trying to cluster with stuff that wasn't quantitative. So it wasn't working, and I was like, no, and then my brain fried itself. But let's go ahead here, bring up some notes, take a look. Is this the one? I don't want this one. Let's go to the mega notes. The mega notes are the best. And let's see some dendrograms right here. Okay. So with these dendrograms, let's go ahead and take a look at them right here. Not nearest neighbor, k-means clustering and hierarchical clustering. Not k-means. Here we are with some dendrograms. Here we go. So this is a dendrogram right here, and we are cutting it for 3 clusters. As far as I'm on the homework, awesome. Keep working on it while you're getting your oil change. That's awesome. Good to see you, Charlie. So if you notice, we have 3 clusters right here, groups 1 and 2, or points 1 and 2, points 3 and 5, and points 4 and 6. So when we do this, let's go ahead and look at a bigger clustering scheme with 4 clusters, and we have all the points. These are the points, as in they would be right here, and we have 4 clusters. We could have done 2. So you can do it where k equals, that's one way. There's a few ways to cut the tree. You can cut with a certain amount of groups, or you can cut at a certain height, and it'll do the cluster assignment of IDs. So basically, have you already made the dendrogram, Amber? I don't want to completely do this problem. My goal has been to do the problems a little bit less and less to kind of help people out. Have you made your dendrogram yet? Because as soon as you've made the dendrogram, you're pretty good to go. Awesome, you have the dendrogram. So once you have the dendrogram, all you want to do now is you want to take, I'll drop the code in the chat. So you want to use cut tree. I always make a typo when I'm doing it. Where's cut tree? So you want to use cut tree, and you just want to choose right here the name of your cluster, and you want to use 5 clusters, right? So whatever you called it. But here's the thing. You then have to assign it somewhere. So what is this? When you run this code, what does it output? It outputs a vector, right? So now that it's outputting a vector, you need to append that vector onto your data frame. So we need to take this vector here and append it onto the backside of our data frame. How will we do that? Well, any variable we want to write in R, any variable we want to put on here, if we want to go to ex4 bike and we go to new variable, we can put it as the last variable on the data frame, and we can append this on. If you notice now, I have new variable and it's all number 4. So when you use the cut tree, you can put the cut tree right here. I think I still have cut tree in here, right? So you can use the cut tree because it will create a vector, and then you can append it onto the data frame. Is this making sense, Amber, right here? What to do is that you'll go to the data frame you're using, you'll create a new variable, and then you'll use the cut tree with how many ever clusters you want. You'll define the name of your hierarchical. Yes, exactly. That's what, because I didn't want to do the whole thing. I want people to kind of see and be like, oh, that's what we do. I was like, how do I do this but not do the problem? But now you should have it. And then once you do this right here, you can just go to table and take the variable, and they're all the same. I made it the same right there. So you can make a table of the variable here and see the cluster IDs. You can also do a summary of the variables. There's that code's in here too. Here I could do some fake cluster IDs. Watch this. Let's go here to, I wonder if this will do it. No, that didn't do it. What if I do this? New variable. If I do that, it's all 1. Let's go rep 1, 2. Let's rep the vector 1, 2, 3, 4. Did that do it? Rep. Replacement has 4 rows. Yes. Oh, and it has 1440. So that'd be, we can't rep it partial time. Oh, we'll do it 2. So then 212. Rep this 212 times. Okay, good. Now we have 2 different groups. Wait, what? Rep 1, 2, 1, 2, 1, 2. What am I doing wrong? Rep this 212 times. New variable 2. Has 2, oh, 2, oh, okay, I get it. So, my brain, just sometimes. So this needs to have, replacement has 200, data has, oh, there we go. So this needs to have 07, there we go. So that should do it. And now I create a new variable 2, of course. So we want to put this in new variable 1, new variable 1, there goes the table of that. And now let's show some really cool stuff right here with the aggregate. So the aggregate, well, it's easy enough to use. We don't need to grab the code. Aggregate is going to do y tilde x, and you can do multiple x's, comma, data equals. And so we are going to use aggregate right here with a y variable we want to talk about, like demand. If we want to do demand, and we can look at, so these are variables we want to look at, avg temp, and we want to look at new variable. And then we need to put in one last argument here, which should be fun equals, and should be capital FUN, fun equals mean. And I think, there we go. X is missing with no defaults, new variable. Did I make a mistake? There we go. Sometimes they want you to put the parentheses, sometimes they don't. Every argument works differently. That's the problem. Try to memorize them all. It's always tough. So we see here, I did new variable also. Oh, yeah, we want to, wait a minute here. We want to analyze the y variable of demand and average temperature. And here it is. So we're aggregating demand plus, oh, let's just do demand. Aggregate demand by that. We should be able to, I guess it is new variable. Wait a minute here. Tilde demand. That's not what we want. Is it aggregating that way? All of a sudden your brain just jumps out of your head for a second. Should be able to get the aggregate. Here's the aggregate, tilde dot. No, I think it's working fine. It is working fine. Can you also go over 3D? Sure, let's take a look at 3D here in a second. You bet. So it is working fine. That's not what we want. Yeah, because we want a new variable. There we go. Wait, what? 2 seconds. New variable. Is my new variable wrong? Oh, is it because it's numeric? Doesn't like it? That should be fine. 2 seconds here, everybody. You ever have one of those moments when your brain just jumps out? Because we should be analyzing it's y, it's dot tilde y, reversing it. So, because we're using the new variable to explain all the y's. Obvious. Yeah, obvious. Sorry, I was doing it right originally. If you go way back in time to when I first wrote it, the first time I wrote it was right here. So here's the first time we wrote it. And then we did that. Then we run this. And we should just analyze it's dot tilde x. Now what this means right here, and I was just a tiny bit confused because it's sending the rows around on me. It's just printing it twice. It's the new variable ID. So what is this analyzing right here? New variable 2. That's even more confusing. So this right here is all the y variables we're trying to understand, and the x variable is how we're separating them. So we're using the new variable here to explain, and then what do we have? All the y variables are what we want to understand. So the y variables are what we're trying to understand, and the x variable is explaining it. So we're only using one explanatory variable, and the y variables like demand, average temperature, effective average temp, average humidity, average wind speed are the y's we want to understand. 3D, what does 3D say? Ah, yes, the ideal clusters. So for this one right here, we're going to replace the 5 NAs, and we're trying to get 5 suggested clustering schemes. So our goal right here is to replace the 5 NAs to get 5 suggested clustering schemes. Now, what should a good elbow plot look like? So Sean, what should a good elbow plot look like? What should a good, really great elbow plot look like? What should a good elbow plot look like? Can you describe in words? Let's draw some elbow plots here. We've got elbow plot 1. Well, that's, never mind. Don't look at that one. We've got elbow plot 1. There's elbow plot 1. Good. Got elbow plot 2 and elbow plot 3. Which of these elbow plots is the best? Elbow plot 1, 2, or 3? Which elbow plot is the best? 1. And the sharper the elbow, the better it is. What do you notice about elbow plot 3? What's weird about elbow plot 3? What's weird about elbow plot 3? Elbow plot 3 is impossible because as we increase the clusters, we can't have the plot go back up. So if you were to increase the amount of clusters you have, which you're going from like 1 to 2 to 3 to 4 to 5 to 6 to 7 to clusters, you can't have the within cluster sums of squares go back up because that's what the y-axis is measuring. It's measuring the within cluster sums of squares. So the within cluster sums of squares can only go down, and we don't want to see this kind of slow decrease. The sharper the elbow, the better. So the first ones I drew is actually the best. If it goes down, it really kind of cuts right here. So if you notice, that's where we kind of get this really good elbow plot. So what should you have for yours? What do you think you should be replacing the NAs with? Numbers that create a sharp decrease and a flattening out, or numbers that go back up, or numbers that just kind of go down slowly and approach 0? Think about what you should replace those NA values with such that you would cut pretty much right here at 5. How the plot should look that it would, yeah. Not the mean. Well, if you replace it with the mean, then your plot's going to look like this. Here, we can do that. Let's find it. If we go and replace it with the mean, let's do that. So if we go to mean of ideal And we take them, well, we need to do NA is missing. Oh, I didn't even store it yet. NA remove, wait, what? NA remove equals true. And there's the mean. So I guess you could place that in all of them. But if you do this, what's it going to look like? Let's see what it looks like here. And we need to make it bigger. K not found. Oh, because we didn't do the Ks. And then we need, oh, there it is. So if we replace it with the mean, what do you notice about this plot right here? What do you notice about this plot right here if we replace it with the mean? What's weird about this plot with the within cluster sums of squares? Why is this one impossible? Replacing it with the mean would do what? So this would be impossible. Well, it begins to flatten, but what does within cluster sums of squares do as we increase the clusters? As we increase the clusters, what does within cluster sums of squares must do? And the within cluster sums of squares looks like this visually. We have multiple clusters. Let's say we have cluster of points here, and then we have a cluster of points here, and we have a cluster of points here. So what do you think is the ideal, like if you looked at this plot, what is the ideal K for this plot? What is the ideal K? What is the ideal K? Like the ideal K, the way this looks would be what? The ideal number of clusters, which is the amount of K, or how high K is, would be what? 3. You're exactly right. Nice, Sean. 100 points right there. Great job. Great coming to office hours. So if we do one cluster centered, probably go something like here, and this would be the sums of the squares. The sums of the squares would look something like this, and you'd compute the sums of the squares from the cluster center, and you'd get a number here, something like, maybe this is just made up, like 4,000. And that's with K equal to 1. So with a K equal to 1, you might have 4,000 sums of squares. Now, if you do 2 cluster centers, you might get a cluster center here and a cluster center here. And then you'd compute the within cluster sums of squares for each of these, so they'd each go to their own cluster, and you'd compute how big the squares are and add them up for each cluster. And then you'd maybe get 3,300 with 3,360 with 2 cluster centers. So there's our 2 cluster centers. But then when we go to 3 cluster centers, which would put a cluster center here, a cluster center here, and a cluster center here, we would get this sums of squares, and you would add all these up. You'd add up these squares, because these are like squared areas. And then you'd get something, these are made up numbers, like 1,800. And that would be with 3 cluster centers. Now, if you went to a 4th cluster center, it might put a 4th cluster center somewhere, just hypothetically. Probably it would split this one, and they don't necessarily have to split, but it'd probably do that for 4. And then what would the within cluster centers do? So we use mean, it would create a new cluster. I don't quite understand, Sean. Explain more. I'm explaining in greater detail. So it's trying to figure out how many cluster centers there are with the elbow plot. So the elbow plot will increase the amount of cluster centers to try to figure out the ideal cluster centers and how many cluster centers there are. So as we increase it, we get more and more, like there's more cluster centers. And even though this looks like 3, you can make 4 cluster centers. So now this one probably have something like 1780. And we could go to 5 cluster centers. If we did 5 cluster centers, it might put an extra cluster center here, and they're going to spread out a little bit more. And then what would happen to the within cluster sums of squares? The within cluster sums of squares would do what now? The within cluster sums of squares would do what when we go to 5 clusters? When we go to 5 clusters, the within cluster sums of squares must do what? So with 5 cluster centers, the within cluster sums of squares must do what? Basically, how far away the points are from the middle of it. The within cluster sums of squares must do what? It will decrease. Exactly right. This will decrease again to maybe something like 1776. Yay, references. And now let's go to 6 cluster centers, which might put an additional cluster center down here somewhere. Now they're going to move. You're not always going to get everything in the same spot, but you're going to get a 6th one, and maybe it goes to 1772. So what are you noticing about this? When do you notice that with our clusters, we're kind of getting a leveling off of the within cluster sums of squares? When do we have a leveling off of the within cluster sums of squares right here? When does it look like the clusters are kind of at the right amount? I'm blocking it again. When does it look like the clusters are kind of at the right amount? At 3. And so this is when the elbow plot, if we were to plot the elbow plot, it would look something, we'd put here 1, 2, 3, and we would get an elbow plot that went, and at 3, it's basically going to level off right here. 3 is where we see that there's really not much of a decrease after 3. You get some decrease, but it's very minimum. So the elbow plot looks to level off at around 3, and that's because we don't need to create more cluster centers. Now, what if there's, let's say there's 100 points on the screen. If we went all the way down here to 100 clusters, what would the within cluster sums of squares be? What would the within cluster sums of squares be if there's 100 points on the screen? If there's 100 clusters and 100 points, you're close. It'd be so small that it'd be 0. Because, and maybe we need to say there's 1,000 points or something, but with 100 points on the screen, you would have a 0 error. Does that make sense? If you had 100 cluster centers, because every cluster could be right on top of a dot. So every dot would, but that's not what clustering is. But every dot is now its own cluster. Does that make sense? Yeah, so then there'd be no error because the error is how far away are the cluster centers from the clusters. But you don't want to extend this out so far that it's eventually going to reach 0 if you give enough cluster centers. And that's when all the points, it's just, the goal is not to get a perfect thing. It's to create groups that can describe things. And we want only a certain amount of clusters. We don't want 100 marketing schemes. It'd be great to have 3 marketing schemes rather than 100. So does this make a great review here, Sean? So this has been a really good review of clustering. Does anyone else have any other questions? What else are people thinking? I'll go back to, there we go. What other questions are there? We did some 320 review. 201 has their assignment. Let's go take a look at more coding. This is not the answer. See, maybe I should put that on here, like, not the answer. Do not use this. Do not use this. Well, think about it. But you want it to look ideal, though. So you want it to look ideal. So what should it do when it reaches 5 clusters? What should it do when it reaches 5 clusters if you want it to be where your scheme, like, how would it look when it gets to the 5 clusters? Does that make sense? How would it look when it gets to the 5 clusters? What would it do at the 5 clusters? What should it do when it gets to the 5 clusters? What should it do? Think about the ideal plot right here, and then think about what it should do, what it can't do. This is the bad one right here. So this is the bad one. It's the bad guy. And this is impossible. So that one is impossible because we can't have an increase. So we want it to look something like this right here. So this is what it should look like. So start thinking about those numbers to replace it right there. What other questions are there? Is it making sense, Sean? If you have a question, let me know. Let's see, it's such silence. Can we go over some stuff? Yeah, which questions do you have, Charlie? It should have less of a drop. Bingo, Sean, you're on the right track there. You're on the right track. Which one are you working on, Charlie? Let's see. I'm pulling up the assignment right now. There we go. Let me pull up the work. And let's see here. I just want to know what we'll be doing tomorrow. Oh, so the work we'll be doing? Oh, the assignments get a little bit more difficult. Let's go over some of the new assignments right here. Let's go over some of the new stuff. So we're going to take a look at the brand new stuff that we haven't seen yet. We're going to take a look at the brand new stuff we have not seen yet. So this will be brand new work here, Charlie. You ready? A great job working ahead. That's definitely the way to learn it. Okay, this is a tough one to start. We're not going to stuff with that. So this one's great. So this is a better conceptual one right here. This is sampling distributions. This will be our next 2 lectures. It's one of those ones. So this one, I hate to say this, but randomness, I think people can sometimes figure out on their own. This chapter is one of those chapters that if people skip, they do not get it. If people skip this chapter, they do not get it. So, keep on blinking my webcam. So people skip this chapter here, they do not get this chapter. It's do not skip this chapter. So right here we have conditions. You'll hear me talking about this tomorrow. Condition 1, random. Condition 2, 10%. So we'll talk about what these mean in a second. Condition 3, success. Well, no, pause. Pause. And then condition 3, success, failure. Okay, so what are these conditions right here? The first condition is that we randomly select these children. So we need to randomly select our sample. You can assume randomization here. We'll say it on the test. The second condition is 10%, which is counterintuitive. We need to select less than 10% of the population. This has to deal with just the way the mathematics works out, but if you select more than 10% of a finite population, it causes errors in the calculations. So is 153 students less than 10%? I'd say it's less than 10% of all students. The last condition is success failure, which means we need to have at least 10 expected successes and at least 10 expected failures. The way to do this is to say if we have 153 children, then with a 12% nearsighted rate, we'd expect 18.36 to be nearsighted, and 153 children, we expect 0.88. Now, Charlie, review question. 0.88 and 12% are what of each other? 12% and 0.88 are what of each other? So this is just a review of probability now. 12% and 88% are what's of each other? They are what values of each other? Complements, exactly right. Great work there, Charlie. These are complements. So you're saying we expect this many children to be nearsighted. We expect this many children to be not nearsighted. Does that make sense? Like either someone's nearsighted, like me, or not nearsighted. So I expect 12% of children to be nearsighted. I expect 88% of children to not be nearsighted. So out of the 153, do we have at least 10 children who we'd expect to be nearsighted and at least 10 children we expect to be not nearsighted? That is the success failure. Yep, and they're also disjoint. So as we were talking about today on Discord, everything that is a complement is disjoint. Not all disjoints are complements though, because think about this. You can make an A in a course, you can make a B in a course, and we're just talking one grade. Like in stats, you will make an A or a B, like of 2 possibilities. Are A's or B's disjoint? In statistics, when you get your grade at the end of the semester, is an A in the class or a B in the class disjoint? Are those disjoint? Those are disjoint. Are A's and B's complements of each other? Are an A and a B complement of each other? Are they a complement? Are A's and B's complements? You either A's and and then A or not A would be a complement. So A or B are disjoint events. A or not A would be complements. So not all disjoint events are complements, but all complements are disjoint. Does that make sense? Because you can't get an A and a not A. So if something is a complement must be disjoint because you can't be A and not A. Does that make sense, Charlie? How all complements are disjoint, but not all disjoints are complements. Hopefully that makes sense. It's a good review and good practicing what the terminology means exactly. Great practice, yeah, because we were talking about this today, and that one question was a little bit tricky. So now that we pass all the conditions right here, does it assume these children are typical to satisfy the randomization and the 10% success failure are met? Yeah, I think it's assume. Yeah, I hate when you have to assume stuff in these. So now here is where it seems a little bit tricky, but here's the formulas you need to know. So when we do this, this really comes down to notation. So getting an A or B is not a compliment, but because you could get C. Yep, exactly. Because there's more things other than A or B, because A and B is not every event. If you could only make an A and a B or A or a B in a class, they'd be complements, because either you make an A or a B. But since there's more grades you could make, A and B are not every single event. And so complements need to encompass everything. Like imagine you go to a party and they say you can have ice cream or chocolate. So you have to get ice cream. You're gonna either put down ice cream, or because they're not gonna let you not put it down. So if what would be the complement of chocolate? It'd be, oh, I said ice cream or chocolate, vanilla or chocolate. So you can only get vanilla or chocolate at the party. And so if you put down chocolate, then the complement of that is vanilla, because you can only put down chocolate or vanilla. But in the real world, the complement of chocolate is not chocolate. So because you can get many other things than chocolate. But if for some reason the only two choices are A or B, then the complement of A would be B. Does that make sense, Charlie? Like, let's say someone says to me and my brother, one of you is going to win the lottery. So either my brother wins or I win. So if my brother doesn't win, I win. So, wait, so that would be a complement vanilla. Only if they're the only two choices. If the only two choices possible, like if you list the sample space right here as the probability of chocolate is equal to 50%, and the probability of vanilla is equal to 50%, then the complement of chocolate is vanilla. Because if someone doesn't get chocolate, they get vanilla. But then if you change it and you put strawberry in there, so if we go here and do probability of strawberry is equal to like 10%, then if you want to talk about the complement of chocolate is vanilla or strawberry, which has a probability of 50%. So just depends on how you talk about it. But the easiest way to talk about a complement is either someone gets chocolate or not chocolate. So, but maybe you're talking about what people will get, and you say either people get chocolate or not chocolate. Not chocolate is defined as vanilla or strawberry. So, and so here the complement is two possible things, because there's three total things. So the complement is everything but this. So the way to think about the complement is like not this, and then you just look at the remaining things, and that's the complement. So what's the complement of strawberry? The complement of strawberry is not strawberry, and so it has a 90% probability of these two. Does that make more sense, Charlie? And so all of three of these are what of each other, though? So the complement would be everything not chocolate exactly. So the complement of chocolate is not chocolate, and then every single one of these events is what of each other, according to the way I've written them out right here. Every single one of these, if you were to compare chocolate to strawberry, strawberry to vanilla, they're all disjoint. Yep. But they're not all complements, because vanilla and strawberry don't equal 100%. Complements must be everything but that event. So how do you know if something's a complement? Well, one, they both can't happen and they equal to 100% probability, because it's either this or this. And the easiest way is to say vanilla or not vanilla. If you can only have one flavor. Exactly. And so then there would be no, I guess you would just have that flavor or not that flavor. But if everyone gets that flavor, then I guess the probability of the complement would be 0. Because if you said, this is a weird scenario. I never even thought of this one. Let's say, well, it's like if you go to this party, it's like one of those parties where they already like make the cup of ice cream for you, and they just make a cup of ice cream for everybody. You just think about how this look in the real world. So you might say, well, I didn't eat it, so is the probability really 100%? But what's the probability if you go to this party, you get chocolate, then it'd be 100%. And then you could say the probability of not chocolate, and I'll do it in notation format. To do notation, you do not like that, and then the probability of not chocolate would equal 0%. So prepackaged ice cream, exactly. So now the probability, the complement there written as not, and that's the mathematical notation for the complement, is 0%. Yeah, exactly. And so, yeah, and that's the thing. If you randomly grab one, especially with those little pre-packed cups, man, I like those little, the things you miss, those little pre-packed cups of ice cream, little circular, you know what I'm talking about? I can't draw a sphere or thing. It's a little cup like this. It's got the little stick on it. It's got that little wooden stick, and you just like eat the ice cream. Oh, so good. I mean, like, it's not great ice cream, but yeah, you miss those things from your childhood. Like Fun Dip. I think I like Fun Dip, and then I get a Fun Dip, and I'm like, yeah, it's like powdered sugar. I don't understand the mathematical notation. Yeah, it's easier if you write out just as words usually. If I just write something like probability of not chocolate. So the probability of not chocolate right there is 0. Because either someone gets chocolate or not chocolate. And so the probability of not chocolate is 0. Actually, you know what? I think the not, someone's going to get mad at me. I think the not goes right there to be exact. So much for my mathematical connotation. But I guess it'd be not the probability of chocolate or probability of not chocolate. Like in chapter 12, it was easier for me to just do the math instead of the notation. Yeah, it can be a lot easier, and just trying to think about it as words can help too. But that's what's causing me a problem because I don't know when to use the rules. Oh no! So when you have, here's a really weird scenario worth mentioning. We'll talk more about probability here because this is a really good review for our last 11 minutes. When you think about the probability of strawberry, probability of vanilla, if these are disjoint events, then, and we've put this type of question on the test. If these are disjoint events, then what is the probability somebody gets strawberry and chocolate? If these are disjoint events, what is the probability someone gets strawberry and chocolate? If these are disjoint events, what is the probability a person gets strawberry and chocolate? So they say it's a party, and you just think about a party, and they're like, hey, we got enough ice cream for everybody. Go grab one off the table. What's the probability you get strawberry and chocolate? Be careful. That'd be the probability you get strawberry or chocolate. So that'd be the probability you get strawberry or chocolate. So if you get strawberry and chocolate, you're getting them both. But since they're disjoint, what would be the probability if they're disjoint? Since they're disjoint, be careful. But if they're disjoint, that means they're dependent. This was a huge trick question. This is why I bring this one up. I try to give some of the hardest questions I think I can remember. Since they're disjoint, just imagine you're at this party, Charlie, and they say, hey, go grab an ice cream off the table. Go grab a ice cream off the table. And you say, what's the probability I get strawberry and chocolate? And it's not a strawberry and chocolate ice cream. It's a strawberry and a chocolate. And they say, go grab a ice cream off the table. I sound like the parent now. Gosh, I need to stop this. They say, go grab a ice cream off the table. What's the probability you get strawberry and chocolate? So they're disjoint events. You can't. Exactly. So what does that mean? If you get chocolate, since they're disjoint, if you get chocolate, what's that mean about getting strawberry? If you get chocolate, what's that mean about you getting strawberry? Since you got chocolate, what's that mean about strawberry? It means you did not get strawberry. Does that make sense? No strawberry. Since they're disjoint, knowing you get chocolate or knowing you get strawberry means the probability of chocolate is 0. So since they're disjoint, if one happens, the other can't, which means they're completely what of each other? Disjoint events are completely what of each other? They'd be completely dependent. Getting chocolate would depend if you got strawberry. Getting strawberry would depend if you got chocolate. So this violates the rule of independence for multiplying probabilities. And then we can also understand theoretically, since they are disjoint, if one happens, the other can't. And then we can understand the probability is 0. It's probably one of the trickiest questions we have. So I might be giving away a test question right now. But if two events are disjoint, then you can say, well, we can't multiply them together, but you can understand theoretically if A happens, B cannot happen. It's like this. The probability of, like, think about this example. The probability of the Red Sox losing a game, what if they said grab 2? Oh, yeah, let's do that. What if they said everyone gets 2 ice creams, go grab 2 ice creams? What's the probability you get chocolate and strawberry then? You just run up to the table and you just grab 2 really quick because everyone's running over. It's like a mad rush. You don't even see what you grab. You just grab 2 ice creams. So there's a 40% probability of chocolate, 40% probability of strawberry. You just grab 2, and they're all arranged randomly on the table. They're not like in a spot and you don't grab 2 in one spot. They're completely independent of each other. Would it be so if you're grabbing 2 ice creams, getting chocolate and strawberry would have a probability of 16%. The probability of getting chocolate and strawberry would be, and truthfully, let me think here. The probability of, I think we stand corrected on this because due to the combinations, the probability, this one gets a little bit more complicated, and let me explain why. The probability of you grabbing A, we'll list them all out right here. You ready? We're going to write the sample space. The probability of getting chocolate, then chocolate, is 16%. Let me use the other pen. It's darker than this one. The probability of you getting chocolate and then chocolate is 16% because that's 0.4 times 0.4. The probability of you getting strawberry and chocolate is 16%. The probability of chocolate strawberry is 16%. The probability of, so we've done all, and then we do more chocolate. chocolate vanilla is 0.8%. The probability of vanilla chocolate is, and I am doing that correct, right? Yeah, I am. 0.8%. Vanilla strawberry is, and then we knew strawberry, vanilla. Vanilla strawberry is 0.08. Strawberry vanilla is 0.08. I'm just multiplying the numbers. And then strawberry is 0.16. And then chocolate is 0.04. Now, the way we'll know we left something out for chocolate vanilla, so chocolate, yeah, 0.08 for chocolate vanilla. Do you understand why? Because chocolate vanilla, and we did vanilla chocolate too then, right? And we did chocolate, strawberry chocolate, strawberry, chocolate vanilla chocolate, strawberry. I think we got them all. Strawberry, chocolate, so many flavors here. And that looks right. I think there should be 9 combinations. And yeah, chocolate is 0.4 times 0.4. So here, I'll put it right here. So for chocolate is 0.4 times 0.4. My gosh, what happened? So chocolate is 0.4 times 0.4. And then vanilla chocolate is 0.2 times 0.4. Does this make sense where the number's coming from, Charlie? And if we add these all up, we should get 100%. 16 plus 16 plus 16 plus 0.08. What's the 0.04 then? It's from chocolate. Oh my gosh, Charlie, 1,000 points. This 0.04 right here should be vanilla. So sorry about that. I messed it up. That was my error. Thank you, Charlie. 1,000 points. I didn't even realize that. So 0.16 plus 1.3 plus 0.08 plus 0.08. 3. Yep, we got it. And then, so we just added all these up. And yeah, so no, you're right. That's a vanilla right there if it's hard to read. That's the probability of getting vanilla. So the problem with this one is there's a repeat. Like you could get strawberry chocolate or chocolate strawberry. So if you say, what's the probability I get first grab strawberry and then grab chocolate, it'd be the probability of that. If you say, what's the probability I get strawberry chocolate or chocolate strawberry? Now what can you do to these? Because these are disjoint right here. When you grab your 2, what is the probability of getting strawberry chocolate or chocolate strawberry? And we just listed out the sample space right here. What's the probability of strawberry chocolate or chocolate strawberry? And sorry about that typo on my part. Mike sometimes makes weird noises. What's it doing? Do you guys hear that? So weird. Don't make weird buzzy noises, Mike. Don't multiply those two together. Don't, this would be, because this is the or. So when you hear or, what should you do when you hear or? Like if I say, what's the probability you get strawberry chocolate or chocolate strawberry? And good work, Charlie. Excellent work practicing this today. It's a little tricky. If we say, what's the probability you get strawberry chocolate or chocolate strawberry, we're asking if they're disjoint, and then we're going to do what with them? Yep, you got it, Charlie. And so the and word, when you hear and, anytime you hear me say and, you multiply. If you hear or, addition. So that's the key thing, and I think the easiest thing, because we'll end with this. So if people are watching this right now, a lot of people use the office hours. Thank you so much for everybody. Lots of people I notice. Office hours sometimes get a lot of views. So this has been a really good review right here. Let me pull up the video. And we need to go to class yesterday. Let me pull up the class video for randomness to probability. Here we go. And let me turn off the audio. And we showed it at the end right here. And we did the compliment, right? There we go. Okay, here we are. No, Brian Inception time. So there we go. And so let's go back to here. And there it is right there. So I'm probably right on top of the Inception part of it. Yes, look at that. Same spot as yesterday. So here are the rules right here. Does this make sense, Charlie? These are the rules. I'm not even near set anymore. I'm just here for a nation. Yeah, Keaton, what's up? Good to see you here, Keaton. Man, we love that. Got some new stuff. All this right here, just a review. Really good stuff right here, Charlie, to make sure you have it. I'm heading off here in literally seconds, Keaton. So good to see you, though, Keaton. Thank you so much. Stat Nation, Mewbot knows that. We got a new Mewbot. Is that the right quote for it? Am I done the wrong quote? Stat Nation. We'll see what else Mewbot has to say. But make sure to have these notes right here. I'm just Brian inceptioning right now. Does this make sense here, Charlie? Have these down. Know the rules. I know, right? But that's got it. I'm going to head off here and start to prepare to teach. But great review. Great work, everybody. I'm going to head off. Charlie, excellent work. Good seeing you, Keaton. Swing on by anytime. We'll be back soon. You'll try. Great work, Charlie. See everybody later. Bye.